Hi guys, hope all of us are doing great. My name is Ernest and this is Ernest Sciences and Mathematics TV channel. Today we are going to look at a concept under radioactivity, and this basically is the concept of a mass defect. And this concept of mass defect is going to borrow heavily from the earlier videos we had done on the concept of radioactivity, whereby we had said that radioactivity basically is a mass transformation processes which of course occurs in the nucleus. In this specific sense, then therefore the concept of mass defect is going to be an evaluation of this specific aspect of the mass that is contained in the nucleus and some of the calculated values for the mass that we're going to see. So therefore, basically, mass defect is the difference between calculated values of the atomic mass and the weight, or rather the weight values of these specific masses that we're going to give in terms of a relationship. So therefore, if you try to look at a specific example, we can be able to give this illustration for mass from the general expression we had given for an element, whereby we say that we can be able to symbolize an element or an atom using this specific symbol for X, and then we can be able to give the atomic weight and atomic numbers using A and Z respectively. So if I can just be able to give a summary, this is the atomic mass, which basically is the number of neutrons plus protons which are contained in a specific atom, and then we have Z, which is the number of protons contained in that specific nucleus. So therefore, we are going to see also that X is going to represent the element. And in us trying to have this specific relationship, then therefore we say that we can have mass of the nucleus represented using this specific symbol, whereby we say that this, of course, is going to stand for the mass number. Or in a specific case, we're going to use this specific symbol in our discussion in representing the mass number, which we have said, of course, can be represented as A in this specific case for this symbolic form of an atom. So if we try to consider the mass of an atom, then therefore we can be able to give an expression using this specific symbol for mass of an atom as capital M subscript A is equivalent to the number of protons, the mass of the protons which are contained in that specific atom, and the mass of the neutrons which are contained in that specific atom given as A and Z respectively. So in this particular case, I've chosen to give it as a mass of a proton. I'm going to take this specific example for an element, or rather for an element of deuterium, which basically consists of one proton and one neutrons that I'm going to use in this specific illustration. So therefore, N is going to represent the number of protons, as I've said, in this specific case for that one, and then Z is going to represent the number of protons in this specific case, and I'm going to use N to represent the protons respectively. So therefore, I can just give this one as another additional N here, which is going to represent the number of neutrons, so that I can create a distinction between these nucleons for the neutrons and protons respectively for Z and N. So therefore, N is going to represent the number of neutrons, and then Z is going to represent the number of protons. And the one that I've indicated for MH, this is a proton, of course, which I said I'm going to consider this a particular isotope for hydrogen, which is a deuterium, which I've given in this specific case. And I've said that this deuterium is going to consist of one neutrons and one proton, which are going to form, of course, the nucleons of this specific atom. So for this deuterium, I'm going to have the mass number or the measured mass being given as, we just give this one as a dry expression. So I'm going to have the mass number of deuterium being given as the mass of the proton plus the mass of the neutrons. I've just given deuterium for a simple case so that it can be able to assist us to simplify this specific concept of this mass defect. So this is going to, we're going to have specific figures which are going to be the mass of a proton, which is a constant. So this 7825 plus. So these particular figures that I'm writing on the board, they are given, so we do not need to memorize them. So these are figures which are going to be given, plus 1.008 and then 665. So this is the mass of the proton and this is the mass of the neutron. I'll say that we're going to consider deuterium, whereby we're going to have this one, of course, given us. So this is an isotope. So for deuterium, we're going to have that too. So it's going to be this one that is going to be given as such. So we have one proton and one neutron given as such. So this value is going to give us 2.0164. So this is 49 in terms of atomic mass unit. So sometimes we may find this one being given as U, of course, which is going to represent what we refer to as a Dalton. If we try to remember that John Dalton is one of the founding scientists who, of course, described the concept of the atomic theory. So some of the symbols, as we have said in some of our videos, are going to be given in order to give credit to historical contributions of this scientist. So this is going to be given as a Dalton whenever we give this one as U. So therefore, it's going to be an atomic mass unit that is given in terms of a Dalton. So therefore, this particular figure that we have obtained for 2.01649 is referred to as a calculated mass. As we have seen, we have done an evaluation, but we are going to have in some instances whereby we are going to have, so this is calculated, we are going to have some given mass, as I've said, which has already been measured. So for this one, for deuterium, this has been measured and found to be 2.0141024. So there's a difference that exists between this given mass and the calculated mass that we have found in this specific case. And this difference is going to be given as the change in mass of that specific atom is given as the mass of that atom, and then minus the mass of the neutrons plus the mass of the protons, which is going to be given as such. So in this case, we're going to see that if we try to choose an atom, an arbitrary atom, we're going to find the difference, this difference in mass between these specific two. Now for deuterium, we can be able to do a calculation and of course find out that the difference between this calculated mass and the given mass is around, so this is going to be around 0.002388 Daltons. So this implies that this difference in mass is going to be illustrated using this specific symbol for delta MA, and this is going to be referred to as the mass defect. So therefore, we can be able to define the concept of a mass defect as the difference between the calculated mass of an element and the mass of the protons and the neutrons given as such, which is referred to as calculated mass. So this in an essence gives us a clue on what the concept of mass defect is, and we're going to see in our later videos that there's a relationship that is going to exist. As we said, the radioactivity is a mass transformation process. There's a relationship that is going to exist between the mass defect and the energy that is going to be liberated or evolved during the radioactive process. This relationship is going to be given using Einstein's energy mass relationship, which is going to be A is equals mc squared in terms of electron volts. So we are going to see that one later in a different video. But of essence for us is to try and identify a procedure that we can be able to use to calculate this aspect of a mass defect using this general formula that I've given on the board. So therefore, if you try to look at this, this is going to be given mass, and the mass of the neutrons and protons as calculated from this specific example. So therefore, these are going to be constant in some of the areas since we have seen that this specific isotope, this deuterium, is going to have this one proton and neutron. So as the protons and the neutrons increase, we are going to see that this can be multiplied by specific integer values depending on the number of neutrons and protons. So sorry for that. So for the number of protons, since a proton has this mass and the neutrons for this specific mass, so as this numbers increases, and therefore we're going to see a different value for calculated mass and the given mass for different elements apart from deuterium, and that is going to give us the mass defect of various elements, which of course I've said that we're going to use heavily in trying to find energy that is evolved during radioactive processes. So check in our description boxes for various videos on radioactivity and some of the concepts that we have discussed which are related to this specific video. So that is it for now, guys. Bye, God bless.